the qubit whose parity is protected by preserving, whose coherence protected by preserving the fluxon parity in the loop.
Are you sharing something right now?
Oh, sorry. Not yet. Apologize. No?
All right, perfect. Yep.
Okay, sorry about it. Just a second. Yeah, so before I start, I would like to thank the organizers for inviting us to share our results to the community, and also I thank all the previous speakers for nice talks, and I think all our talks complement to each other. So I'm trying to add some more understanding and share our results. So I'll start with our design of the bifluxon. I'll discuss the parameters which offer simultaneous protection against decay and dephasing. I'll present our proof of concept experiment. I'll demonstrate the ability to turn protection on and off, and order of magnitude enhancement of T1 time in protected regime, and also I'll discuss the further steps that might improve the decoherence times of the qubit. So this circuit of bifluxon is essentially the fluxonium, where the single junction is replaced with charge-sensitive Cooper pair box made of two identical adjacent junctions. The shunting inductor has inductive energy EL and charging energy ECL. This circuit has two Noonan knobs. That's the gate-induced charge on the island and the external flux in the loop. During this talk, I'll use reduced numbers. So the charge 1e on the island corresponds to ng equals to 0.5. So if you want really deep theory on this circuit and on the qubits made of this, I put here some references. Here I'm going to give you just a simple intuition how this qubit works, what the origin of the protection, what are the required parameters, and so on. So the reduced Hamiltonian of the system is here, and here we consider only two lowest charging energy, charging states of Cooper pair box, represented by this sigma z. And the most interesting case is then the charge on the island is exactly 1e, and this term drops, and Hamiltonian becomes more simple. It's diagonal in sigma x matrix, and actually our system is equivalent to two fluxoniums made of single Josephson junction, but with this 4 pi periodic potential, and the sign of the potential is defined by the state of Cooper pair box, symmetrical and asymmetric. And it's easier to understand that the lowest states of the qubit are the product of symmetric and asymmetric charging states, and the fluxon-like wave function localized in the potential minima near even or odd numbers of 2 pi's. We'll see later that depending on the circuit parameters, it should be many components of the in this fluxon state, but for us it's important that they are distinct by the parity of the fluxons in the loop. It already gives us some intuition about the protection of this system, because the logical states are encoded in these combinations of charge and flux states, charging states are orthogonal. Fluxon states are almost orthogonal. And the rest of the states, non-computational states, have a much higher energy. So we need the correlated noise in two channels, charge and flux, in order to induce this bit flip. And in this sense, it's similar to the idea of composite qubit introduced yesterday by Will Euler. More quantitatively, it was discussed already that decay rate is proportional to matrix element squared. Now we have two channels, phase matrix element and charge matrix element, and you can see that by approaching to this point, charge point ng equals 0.5, flux matrix element goes to 0 pretty fast, and charging matrix element remains non-zero, but its absolute value is suppressed by this exponential factor. Actually, this is given by overlapping of wave functions in flux representation. Let's take a look on the bands of this qubit. It consists of the parabolas with the curvature inversely proportional to the qubit inductance. Each parabola corresponds to the certain number of fluxons in the loop: 0 fluxon, 1 fluxon, 2 fluxons. And important feature here is that neighboring parabolas intersect. There is no avoided crossing here, and we can interpret this as a result of Aronoff-Kesher interference, so imagine that we have fluxon and it has two paths to enter, to tunnel into the loop through those two junctions, and provided the charge on the island is exactly 1e, the phase between those two processes is pi, and we have destructive interference, right? And so the resultant amplitude of single phase sleeves is 0, right? But in contrast, if we have two fluxons here, the interference is constructive for that process, and that opens the gap between parabolas of the same parity. And the gap size tells us about this double phase sleep rate, which is also pretty small, exponentially small, and defined by overlapping of the wave function of the same parity. So we can say that our qubit is sort of cosine phi over 2 element, and it supports the correlated transport of pairs of fluxons. And it belongs to the same family of parity protected qubits that been discussed today. Similarly as 0 pi, all these are Aronoff bomb qubit, which is charge parity protected qubits, where cosine 2 phi element provides 4e transport. Right? So, and as we already learned today, in order to have low dephasing rate, we need suppress the curvature of bands of dispersion, and similarly to transmon. And to enter this limit, we need to have tunneling energy, which is EDPS here, double phase sleep rate, to be dominated over to be much greater than kinetic energy, which is EL, right? That leads to flat bands, but also associated with large quantum fluctuations, right? And we have many components of fluxons in the wave functions, but it's important that overlap between them remains small, right? Because they reside in different subspaces, just joint regions of the space. And it's important that for regular 1D qubits like transmon, this delocalization leads to increase of matrix element, right? And I should add, it's true only for static Hamiltonians, as we learned from Andrew's talk. Time dependence might help as well. So it allows us to formulate the requirements for optimal bifluxon, which would provide simultaneous protection against decay and dephasing. So in order to suppress single-phase sleeps, the symmetry of the junction should be small or 0. The ratio EJ over ECL should be in order of 10 to have these narrow components and ensure its low overlap. But the number of components should be large in order to enter this transmon or flatband limit. And these last condition is pretty hard to satisfy, because our estimation says that we need like tens of microhenries. So in this particular experiment, we aim at demonstration of T1 enhancement, but don't expect much from dephasing times. And even with our fabrication limitations, we were able to demonstrate order of magnitude enhancement in T1. So this slide shows the layout of our experimental sample. Cooper pair box in red forms the loop with superconductor implemented as a linear chain of single Josephson junctions. In blue, the qubit is inductively coupled to a lumped element resonator, and offset charge on the island can be varied by the voltage biasing of microwave transmission line. External magnetic field sets the flux in the loop. So we know that superconducting devices are affected by quasi-particle poisoning, especially in charge-sensitive devices. It results in so-called I pattern in first tone spectroscopy. It means that quasi-particles tunnel on the island on the time scale of measurements, and we observe two states distinct by 1e in the same time. So an important feature of our design is the proper gap engineering. We fabricated the central island with a thin aluminum layer, which superconducting gap delta is higher by 0.3-0.4 K in comparison with the deltas of the side electrodes. And we formed the potential barrier for non-equilibrium quasi-particles, and they cannot tunnel anymore on the island. As a result, we get rid of I pattern, and actually we observe only one quasi-particle event per like 20 minutes. In order to see I pattern again, we have to increase the temperature and thermally generate quasi-particles. So our system is quiet enough to perform standard two-tone measurements. Here you can see the qubit 0-1 transition as a function of external flux for two values of the charge on the island, 0e and 1e. It reminds the spectrum for fluxonium, where this slope is inversely proportional to the inductance of the loop. And the transition energy at this point, full flux frustration, at 0e corresponds to this transition energy corresponds to the single phase sleep rate. At 0E, it's few gigahertz, and it goes down to almost 0 at 1E state in accordance with Aronoff-Kasher picture that we discussed before. The residual phase slips here are due to asymmetry in the junctions. We'll discuss later. Another important feature of these measurements is that dispersive shift decreases when we approach this charge 1E, and the contrast of the measurements of the spectrum also goes low because our dipole moment between 0 and 1 state get suppressed, right? That also indicates that we have that this transition 0-1 becomes forbidden by this parity selection. So we have extracted the circuit parameters by fitting the experimental results to the direct diagonalization of the Hamiltonian. All the extracted parameters are close to expected ones. Only the asymmetry of junctions is a little bit higher than we expect from our standard fabrication abilities, which should be around 3%. But I guess here we just get unlucky. Also, we observed the flux-independent mode with frequency around 14 gigahertz, and we attribute this to the self-resonance mode of superinductor, right? And that means that microwave impedance of our superinductance is 20 kilo ohm. So what about time domain? So in 0E state, unprotected state, we can use just our standard technique for T1 measurements because qubit is coupled strong enough to the readout, and this 0-1 transition is allowed. But in the protected state, we can neither talk to qubit nor read out its state. So the procedure for T1 measurements was following. We started from unprotected state 0E and excited the qubit with this microwave pi pulse. Without the delay, we applied the gate voltage pulse and shift the charge to 1E here, and this process took only like 30 nanosec. And after that, we stored the qubit here in protected state. After that, we removed the protection and read the state out. So these are results for T1 measurements taken at full flux frustration, and you can see it was taken with protection pulse and without protection pulse, and as we can see, there is like order of magnitude enhancement of T1 due to this protection here. But in general, it might be related to change of the qubit frequency, right? Because as we learned yesterday from Vlad's talk, the lower operation frequencies of qubit usually associated with lower losses, dielectric losses, right? So in order to address this question, we performed the session measurements in whole range of qubit parameters, and we can see that regardless the qubit frequency, we still have this significant improvement of T1, and this is the main result of our work here. So dashed lines here are the fitting to the model of resistive noises. Here, blue line corresponds to the decay due to noise in flux channel, and it's responsible for decay in unprotected state, and coupling to charge degree of freedom responsible for decay in protected state, as we saw before. So things are more complicated with T2 measurements. Again, we performed the time domain. We performed T2 measurements for unprotected state and got something like 0.7 microsecond T2. But this previously discussed idea with protective pulses doesn't really work here with our current instrumentations, because as you remember, this shift to protected state is associated with change in the qubit frequency by something like gigahertz, and this drop in the amplitude might be attributed just to jitter in our pulse duration, which is for our current instrument is about 0.3 nanosec. So that kind of measurement gives us just the lowest limit of T2, which is also around microsecond. So in general, but yeah, we don't expect much from this particular design, because again, the charge dispersion was pretty large for this particular sample. And I would like to discuss some ideas how to mitigate this dephasing due to charge noise. So in principle, it's nice to have the control knob, which turns protection on and off. In this case, we don't need to use those long Raman transitions. We can just allow the transition, do whatever we want, and go back to protected state. In our case, this parameter is charged on the gate. In this sense, we lock our fluxon in the loop. But if we have control parameter, we unavoidably have the noise and control parameter. So if the charge deviates from this 1E state, we open the lock. And by this, we got both. We got increased matrix element, right? And we, since we increase single phase slip rate, we increase the energy of qubit, which leads to dephasing. What can we do here? We can, again, as it was discussed before, we can add more locks, right, to the system. In this case, if just one charge on any island is 1E, the flux here is confined, right, and we are protected, and only correlated noise might release the flux. So to illustrate this is a calculated spectrum of two island device, and as you can see, as long as any of charges on the island is 1E, the energy of qubit stays close to 0, and even if we walk around the diagonal, the curvature of this dispersion is smaller, as it was, and as it nicely showed Robert before, we have polynomial protection against this type of noise. So currently we are working towards this device and have implemented the qubit with 2 gates. Unfortunately, it's too early to discuss the results, but I would like to emphasize that we have independent control of two islands. And speaking back about quasi-particles, for example, this picture was taken by about like 10-15 minutes, and we observe only few quasi-particle events here, so it means that our system is pretty stable. So as a result, we introduced the Bifluxon design, which with proper parameters offers simultaneous T1 and T2 protection. On the experiment, we demonstrated the ability to turn protection on and off. That might facilitate initialization and gates of the qubit, and demonstrated the enhancement of T1. So, and the next step is implementing larger inductor. It's like Blockheim from Vladstock, and stacking islands to reduce the charge noise sensitivity. Thank you.
Great, thank you. Are there any questions? All right, we don't seem to have any questions, so I'm going to take this to the